open source tends to win, and we can really crowdsource a lot of knowledge from people with domain expertise. And we hope that this will be the state of the future, and we'll get to open source models essentially, as opposed to closed models, using crowdsourced training. I'm Justus. I'm a researcher at PrimeIntellect, and I'm going to talk about decentralized training in the inference-time compute paradigm. So first of all, what is PrimeIntellect? Some of you might know us already. We work on decentralized training. We're backed by Founders Fund, Karpathy, other cool investors. Just saying that. So in case you want to work for us, maybe you're a researcher working on reinforcement learning, reach out to me. I'll be here at the conference. And essentially, I think the way to summarize what we do, or one of our goals, is compute is this incredibly scarce resource, and we think, in the future, as AI gets more powerful, we'll need a lot more compute, and we want to use as much compute as possible. And GPUs around the world shouldn't idle, right? There are a lot of companies that want GPUs, that want to use them, but actually there's a lot of compute around the world that is idling, right? Like data centers are not 100% utilized. Companies might have, long-term contracts, but they're not using GPUs all the time, like all of their GPUs that they have. And so we're thinking about ways, how can we fix that? And we're kind of building a protocol and orchestration layer that enables this. So first of all, the maybe more boring part of the business is we have a compute marketplace where we aggregate with cloud providers, and anyone who has spare GPU capacity who can onboard their compute to our platform, and we can then resell it as on-demand compute to AI researchers or other labs that want to run GPUs. And yeah, if you need GPUs, feel free to check it out. The second part that is way more interesting, and that I'm working on along with the research team, is research on decentralized training, where we're thinking about, okay, instead of just renting out the compute to others, are there ways we can actually effectively leverage all the idle compute that we've onboarded to our protocol? And some of the use cases here might be training models, which I'm going to talk about in particular, but also synthetic data generation. Right now, we've just finished our dataset Synthetic 2, where we've created a large reasoning data set from the newest DeepSeek R1 model that can then be used to fine-tune other reasoning models. And we're also working on the infrastructure aspects of making that happen. For instance, TopLock is a scheme for verifiable inference, where we can actually verify that if someone claims to have performed a certain computation with a GPU, particularly inference computation, we can actually verify, okay, this particular text was generated from this model, which is necessary if we want to onboard, trustless GPUs. So people using gaming GPUs, for instance, because we cannot always trust these people, right? So this just as background on the company. My talk is about, the inference-time compute paradigm and why this decentralized infrastructure is particularly suited for that. So just kind of to reiterate what I'm talking about here, the inference-time compute paradigm basically refers to this discovery that you can just spend more compute on inference and get better results from models. The simplest form of that would be to take a math question, sample, instead of just one response, 100 responses, and then do majority voting, which will lead to higher accuracy on average. And then, you also have agents, which might use tools and spend more time on inference by just doing a bunch of tool calls and so on. And basically, O1 from OpenAI was kind of this first breakthrough that showed, oh, okay, actually the best way to spend more inference time compute is to train a model to using reinforcement learning to reason for longer, right? And now instead of having a response to a math question that has 400 tokens or so, we have 10,000 or 20,000 token responses, because the model has just learned through reinforcement learning to reason through problems and give then very high quality responses. So yeah, we're definitely making like a long-term bet on reinforcement learning. We think that this is kind of a recipe to hill climb any kind of task you want to optimize for, particularly as you give an agent access to tools like a Python interpreter or the ability to search the web, and can therefore optimize agent workflows end to end. So what I'm going to talk about is why we think reinforcement learning is particularly suited for this decentralized infrastructure. And particularly, I'm making two arguments. First of all, the infrastructure aspect. I believe that, as I said, this infrastructure is particularly well suited for this. And secondly, the open source collaborative approach is also much better suited on the side of collaboratively developing RL environments. So just to start with the first point of the infrastructure, I'm just going to recap kind of what decentralized pre-training looks like. For that, we can take a look at Intellect 1, which was the first model that we trained only through pre-training. And for pre-training, what you have is you have a static data set from which you sample a bunch of batches. Then you perform a gradient update, and then a data parallel setup where you have multiple replicas of your model distributed across multiple compute nodes. You essentially take the gradient update, you average the gradients across all of your compute nodes, and then you perform the gradient update on the full model. This is very communication intensive, meaning that for every training step, all the time, every few seconds, you have to average these gradient updates across your nodes. And in our case, in the decentralized setup, we had nodes not just in one data center, but we had nodes, as you can see on the map, in Europe, in the US, in Asia, and therefore you have super slow connection speeds, right? In a data center, you have an InfiniBand connection, so you have terabits per second of connection speeds, whereas in our setup, we use the public internet, therefore we have gigabits per second, like 2 gigabits or so of connection speeds between our compute nodes, and therefore the internet speed is much slower. We have to communicate much less. We have to find a way to communicate much less to enable training, actually. And so the way that is done is using DiLoco, which just very naively says, okay, instead of synchronizing our gradients every training step, we just do it every 100th or every 500th for every 500th training step. And that works quite well, actually. But it's still like a big modification to the core training algorithm, right? But that changes in reinforcement learning. And why I'm going to explain now. Again, reinforcement learning is different from pre-training because in reinforcement learning, you don't have a static data set, but instead, the LLM that you use iteratively generates its own training data. So what you have essentially is a set of tasks or prompts and ways to verify the responses for your tasks. So that might be a rule-based reward where for a math question you can check, okay, is the number that the LLM outputs actually the ground truth response? Or it can be a neural reward model, which you do in RLHF. And therefore, basically what happens here is you don't just need a lot of compute for the training operation where you do the gradient updates and you have to synchronize gradients, but particularly as your rollouts, so the inference steps become longer and you generate more tokens, which is just happening, right? The reasoning models get smarter as you let them think for longer. So instead of 10,000 tokens, you want to do 20,000 or 30,000, 40,000 tokens. The more that happens and the more time you spend on inference compute, the more of your GPUs will actually be used to generate rollouts and do inference on the models. Just as a rough number, we did a training run for Intellect 2 where we had on average, thinking traces that were 7,000 tokens long, and there 75% of our compute was spent on just inference, so just sampling training data iteratively and not actually the training part. And as models get smarter, as reasoning chains becomes longer, this ratio will just increase, so the ratio of inference to training compute. And so with that being said, inference is very much parallelizable, right? I can essentially take 10 GPUs that are distributed across the world, place a replica of my model on there, and just sample from those models. And I don't need to communicate between these nodes in any way. The only thing I have to do is I have to send back the generated data for training to my training node, but that is super easy, right? Because the generated data is not very large compared to sending gradients, because if you have a 10 billion parameter model and you store your gradients in 16 bits, that means you have to send 20 gigabytes, whereas a few reasoning traces are not 20 gigabytes of data. So that's negligible communication overhead. And using this insight, we've essentially recently trained and released Intellect 2, which was sort of the first reasoning model that was 32 billion parameters large, which was trained using this decentralized infrastructure. And the way this works is kind of depicted here. So as I said, the majority of the compute was inference compute, and this inference compute was onboarded permissionlessly. So we just had a community of people, cloud providers that had idle compute that contributed their compute to our training run. And we only owned and trusted our centralized training workers. So we had one training cluster where we performed the actual gradient updates, and the rest of the compute, so the inference compute, the inference computations, they were performed on all of these decentralized inference nodes that people onboarded to the training run. So as you can see here, the way this works was essentially we had our training nodes. From those training nodes, we sent the current policy weights to this inference nodes, the inference GPUs, which people onboarded to the training run. Then we validated, people generated training data. We validated this training data using TopLog, which I'm going to go into detail about later, so that we could actually make sure, okay, people did not just send fake data, but the data they claimed was generated from the policy weights was actually sampled from those policy weights. And then from the validator, we sent back the samples that were accepted to our training cluster, and then performed the gradient updates, and then sent out the new iteration of policy weights so we could resample training data and basically iteratively improve the model using reinforcement learning. Yeah, and just some details. Basically, if you do this naively, you would think that, okay, at all time, only the training workers or only the inference workers are performing work, because we first have to update the policy weights, then send out the new weights. But what we did was asynchronous reinforcement learning. So at all times, training workers and inference workers were actually running. It was just the case that the inference workers did not have the most recent up-to-date policy weights, but the N-1 policy weight, basically. And so just to go into some technical details, about the asynchrony part, we validated using ablation experiments that you can use old policy weights to generate your training data, and that does not affect the performance of your model. I'm just going to go through these quickly. TopLog is essentially this verification scheme that we use to verify that, okay, when we have a trustless node that from some third party that we can't trust, could be like some person having a gaming GPU in their bedroom, right? We can verify that the data they sent to our training worker was actually generated from the policy weights that we sent using TopLog, which is a very efficient verification scheme, but I can't go into detail here now because of time constraints. Then we have Shardcast, which is essentially a content distribution network for policy weights. So we have our centralized training cluster, and we send out our policy weights to the inference workers, and we do that by just having intermediate relay nodes that we send the weights to, and they then distribute those to the inference workers. And lastly, we have the protocol, which is kind of right now a test net that explores the idea of, okay, can we financially reward inference workers? Because of course, right now people just contribute nodes because they like the work that we're doing, but at some point, there has to be a way to actually, if we want to make this sustainable, to pay people to provide compute, right? And so that is that. So just to recap, using these engineering innovations that I just described, reinforcement learning in a decentralized setting does not differ from a centralized setting. And this is different to pre-training, where, as I said, you have to minimize communication, therefore use tricks like DeLoco. Then my second point that I was mentioning was about the collaborative open source development of RL environments. And just kind of to describe what I mean by that, I think the bottleneck really for reinforcement learning and to get smarter models is the amount of RL environments we have. By RL environment, I mean the reward functions and the tools that you give a model access to during the inference rollouts. And this is basically, and we need RL environments essentially to train the models for specific tasks. So the questions might be, how can we teach models to write fast CUDA kernels? How can we teach them to analyze scientific data sets or to search for information on the web, the same way deep research does it? And for all of that, we have to build essentially specialized RL environments to give the model rewards for the actions it takes. And if you think about it, this is very parallelizable, right? Because it's essentially, to do a single RL environment, you basically just have to grade an LLM output and give it access to tools. And this is something that requires a lot of domain expertise. So, for instance, for the scientific applications, we have companies or organizations like Future House that have recently released a reasoning model for chemistry. And to build an RL environment for chemistry, obviously you need to know a lot about the science. There's Kernel Bench, which friends of mine did, who are a lot into CUDA kernel development. Obviously, a lot of domain expertise required. You might also say that reinforcement learning can be very good for hacking, and for that you need to simulate vulnerable software. Again, domain expertise. And then you even have stuff like simulating white collar work through something like CRM Bench from Salesforce. And so basically the question is, how do you crowdsource, or how do you get to a lot of diverse and high quality RL environments? And I think a much better way to do this than being a single company like OpenAI is to actually do that in the open and to have a repository with abstractions where people can implement their own RL environments, which is really more of a traditional software engineering task. And kind of history has shown that, okay, in traditional software engineering, operating system development, open source, collaborative efforts tend to win. So here, for instance, PrimeRL is our reinforcement learning framework, and this is just an RL environment that an open source contributor has added to it. And I think really, if you find the right abstractions and you can encourage people with domain expertise to contribute RL environments, that is the way you're going to get a data advantage compared to the big labs. So lastly, in terms of our work, some of you might know Verifiers, which is a repository from Will Brown, who also recently joined PrimeIntellect, which does provide these very universal abstractions for making it easy to build RL environments. This will be merged with our training framework soon, and this is kind of the way we hope to encourage as many people and researchers who are already building on top of Verifiers to contribute RL environments so that we can teach models very diverse skills. Just to recap, I talked about basically why will decentralized open source training efforts win in kind of the paradigm of test time compute, which is basically reinforcement learning. And my two main points were most of our RL compute is used for inference, and if we find a way to onboard all GPUs around the world using a protocol like ours, then we'll have a lot more compute for our training runs than even the big labs that build dedicated data centers. And secondly, if we find a way if we have good unified abstractions, building RL environments that teach models, which is basically the training data for reinforcement learning, building these RL environments is really more of a traditional software engineering effort. And I think history has shown that in traditional software engineering compared to AI training, open source tends to win, and we can really crowdsource a lot of knowledge from people with domain expertise. And we hope that this will be the state of the future, and we'll get to open source models essentially as opposed to closed models using crowdsourced training. Thanks for listening.